Layer 4 DR mode is a high-performance load balancing method. DR stands for direct routing. It's sometimes referred to as DSR, which stands for direct server return, and some vendors refer to it as nPath routing. DR mode works by directly routing request packets to the chosen servers. It does this by changing the destination MAC address of request traffic. When using DR mode, reply traffic flows from the servers straight back to the clients. The reply traffic bypasses the load balancer, which maximizes its throughput. The technology behind DR mode was originally developed by IBM in the mid-1990s. DR mode's earliest uses were in 1996, when it was used to serve web traffic for the Deep Blue vs. Garry Kasparov chess matches and the Atlanta Olympics. It went on to be used for the Wimbledon Tennis Championship in 1998 and the Sydney Olympics in 2000. IBM's work was turned into the IP Virtual Server, or IPVS, in 1998. This was done under the umbrella of the Linux Virtual Server Project, or LVS. IPVS has been an integrated part of the Linux kernel since 2008. It provides highly efficient Layer 4 load balancing using a variety of methods, including DR mode. From its origins in the 1990s, DR mode has become a mature, well understood, and widely deployed technology. At Loadbalancer.org, we're the DR mode specialists. We love it because it's the best way to provide peak performance, immense scalability, and high availability for services and applications. Most load balancing methods require both request traffic and reply traffic to flow through the load balancer. This turns the load balancer into a potential performance bottleneck. In contrast, DR mode load balancing allows reply traffic to bypass the load balancer, which maximizes its throughput. Traffic flows directly from the server to the client on the return journey. This is particularly beneficial in scenarios where reply traffic is significantly larger than request traffic. Streaming media is a good example of this, where the reply traffic containing the requested content can be several orders of magnitude larger than the request traffic. Other well-suited examples include medical imaging, back-end storage, and any service where throughput and performance are paramount. Another advantage of Layer 4 DR mode is that it preserves the source IP addresses of clients. This means that load-balanced servers can observe and log the real source IP addresses of connecting clients. This isn't possible with most load balancing methods without making significant network changes. DR mode is used across a wide array of applications to provide scalability and high availability. While it's awesome, there are some scenarios where it can't be used. Firstly, DR mode can't currently be used in the AWS, Azure, or GCP cloud platforms due to limitations in these environments. Secondly, for DR mode to work, the servers and the application being load balanced must be able to accept traffic sent to a specific IP address, which we call the virtual IP address. This can be a problem if an application is only able to listen on a server's primary IP address. The concept of a virtual IP address will be explained later. Finally, because DR mode works at layer 2 by changing MAC addresses, the load balancer and the servers being load balanced must be on the same network segment. Putting a router hop between the load balancer and the servers will break DR mode. There's a niche variant called ton mode which works around this restriction when using Linux or Unix servers, however, that's outside the scope of this video. Let's look in detail at how DR mode works. Here's an example network with a cluster of servers, a load balancer, and a client machine. A Layer 4 DR mode virtual service has been configured on the load balancer. The free servers have been defined as real servers, which are associated to the virtual service. This means that request traffic will be load balanced across the servers. The load balancer has a virtual IP address, referred to as a VIP. When the client accesses the virtual service, it does so by sending a request packet to the virtual IP address using the correct port. The packet arrives at the load balancer, which examines the packet's destination IP address and destination port. As the destination address and port match the defined virtual service, the load balancer chooses a real server from the cluster to handle the request. The The load balancer uses a scheduling algorithm to choose a server. The load balancer then directly forwards the request packet to the chosen server. It does this by changing the destination MAC address of the data frame that encapsulates the request IP packet. The MAC address is changed to the MAC address of the chosen server. The load balancer then retransmits the request packet on the network, and the packet arrives at the chosen server. The destination IP address of the request packet hasn't changed and is still the virtual IP address. The default behavior of the real server will be to drop the packet because the server doesn't own the packet's destination address. In this example, the server only owns a single address, its base IP address on the network. The best solution to this problem is to assign the virtual IP address to every real server so that they can all accept packets that have the virtual IP address as their destination. Consideration must also be paid to ARP, the Address Resolution Protocol, which is used to discover which MAC addresses are associated with which IP addresses. The real servers must be configured so that they don't respond to ARP requests for the virtual IP address. They also must not use ARP to advertise the fact that they own the virtual IP address. These changes are important to prevent IP address conflicts. In our example, the client machine will broadcast an ARP request to all hosts on the local network asking who has the virtual IP address. The virtual address is owned by the load balancer and each of the real servers, but we only want the load balancer to respond to the ARP request. This is because all request traffic must go to the load balancer, so only the load balancer should announce that it owns the virtual IP address. The client's request traffic will then be sent to the load balancer. Configuring the ARP behavior of servers is essential for DR mode to work. This generally involves adding the virtual IP address to a loopback network interface and changing some networking options from the command line. The specific steps vary between operating systems and can be found in our administration guide for Linux, Solaris, BSD, and Windows. After the server has accepted the request packet, it processes the request and sends the reply directly to the client. The source IP address of the reply packet is the virtual IP address, because that was the destination address of the request. From the client's perspective, the reply is from the same IP address that it sent the request to, and so the client will accept the reply traffic. All return traffic from the real server goes directly back to the client, bypassing the load balancer. This eliminates the load balancer as a potential bottleneck. The volume of return traffic is limited only by the available network bandwidth. For 15 years, here at Loadbalancer.org, we've recommended Layer 4 DR mode to our customers. Over the past 5 years, we've started recommending Layer 7 based load balancing in an increasing number of scenarios. As CPUs have become faster and Layer 7 load balancing software, such as HA Proxy, has matured, Layer 7 based solutions can easily scale to deal with large volumes of traffic. While these recent advancements provide more choice in what load balancing methods can be used, we still love and recommend using Layer 4 DR mode for its unbeatable performance, simplicity, and consistency.